So we saw previously that the JGA, or the juxtaglomerular apparatus, was a spot where the ascending limb of the loop of Henle came into contact with the afferent arteriole, and both the cells on the afferent arteriole and the ascending limb are modified there. So we call the modified cells on the nephron loop macula densus cells. By the way, loop of Henle is the same thing as the nephron loop. Sometimes there are multiple names for these, so the loop of Henle and the nephron loop are the same thing. It just happens to be labeled loop of Henle here and nephron loop on some other slides. And juxtaglomerular cells are the modified cells on the afferent arteriole, and this is going to make that juxtaglomerular apparatus, which is going to modify the blood pressure coming into the glomerulus, as we'll see soon. So we want to talk about the filtrate. So again, filtrate is going to be forced out of these glomerular capillaries, should not have large plasma proteins or medium proteins in it, but all other constituents of the plasma should come out into this renal corpuscle, into the Bowman's capsule, which goes out toward the renal tubule. So we're going to look at the pressures, and these should be similar to pressures you have learned in the blood pressure. We've got hydrostatic pressure, which is the pressure that a fluid exerts on the walls of its container, and osmotic pressure, which means fluid goes toward a higher solute concentration. So we've got these pressures that are going either opposing or promoting filtration into the glomerular capillary. So if we force a lot of fluid out, in one day we have about 150 to 180 liters of water that go into all of these glomerular capsules in all of your nephrons. Very small amounts, moving water in small molecules, but about those 48 gallons should be reabsorbed into 1 to 2 quarts of urine, which is very variable depending on hormones, amount of water drank, amount of exertion, metabolic water produced, etc. So filtration fraction is about 20% of plasma. So when we look at this, we get so much filtrate for several reasons. First of all, notice the size of the afferent arteriole going into the glomerular capillaries and the efferent arteriole leaving. The afferent arteriole is much larger, so we've got a higher pressure going in than fluid coming back out, so we're able to force a lot out. Also, if there was just one loop going in and then coming back out to the efferent arteriole, we would not have nearly as much filtrate, but this glomerular capillary bed is a big ball of capillaries, so we're really maximizing our surface area for filtration. So that blood pressure is high due to the small size of the efferent arteriole, and we also can filter out a lot by the sufficient ball of glomerular capillaries jammed into each renal corpuscle. So the glomerular filtration rate is the amount of filtrate into that Bowman's capsule that we can get in both kidneys per minute. So we can learn how to calculate that. The important thing to remember is that fluid has to flow at a certain rate through that renal tubule in order to get a concentrated, adequate amount of urine. So homeostasis requires the kidneys to keep that filtration rate very constant, and this is a very precise mechanism from your body. If that pressure going in is too high, things go through that tubule too quickly, and we're not able to reabsorb the nutrients, water, and ions that we might need. If fluids are flowing through that nephron renal tubule too low, we may not actually even be able to excrete all the waste and other end products that we need to. So it's very important that our kidneys are able to maintain that filtration rate. So glomerular filtration rate is calculated as follows. All of these abbreviations, GHP stands for glomerular hydrostatic pressure, GCOP stands for glomerular colloid osmotic pressure, and CHP stands for capsular hydrostatic pressure. This is going to be very similar to the net filtration pressure you should have learned in the blood vessel chapter. What we're trying to find is our net filtration pressure, and here we see an average is 10 millimeter mercury. But how we get to that, we take pressures promoting filtration, which is GHP, and subtract GHP from both GCOP and GHP. So if you want to write that down, our net filtration pressure equation from the renal corpuscle is NFP equals GHP minus GCOP minus CHP. Now going over what each one of those mean. Hydrostatic pressure, once again, is the pressure that a fluid exerts on the wall of its container. So glomerular hydrostatic pressure is the blood pressure on the glomerular capillaries that forces fluid out into this renal corpuscle. That should be an average of 50, may vary. So that is the pressure promoting filtration, fluid out into the corpuscle. GHOP is glomerular colloid osmotic pressure. This means that due to the presence of large plasma proteins that do not leave these glomerular capillaries, osmotic pressure means that water will follow those large proteins and come back in. So that is opposing filtration as it's pulling fluids from the corpuscle back in due to osmosis. That is therefore not a filtrative pressure, but a reabsorptive pressure. And finally, capsular hydrostatic pressure is the pressure that the fluid already in this renal corpuscle will push back on the glomerular capillaries. Notice that is normally 10. So that is capsular hydrostatic pressure. And like glomerular colloid osmotic pressure, it does not promote the movement of filtrate out, so it is a reabsorptive pressure. So if we put all those numbers in, we'd have 50 minus 30 minus 10. That would give us 10 as our net filtration pressure average here in our glomerular capillaries. So averages for the filtration rate are 125 milliliters per minute in males and 105 milliliters per minute in females. And remember, that is the filtrate produced for both kidneys per minute. That may seem large, but remember, most of that fluid is going to be reabsorbed as it goes through the renal tubule to make urine. So we have about 48 gallons a day reabsorbed to 1 to 2 quarts of urine. Now again, it is very, very important to keep these rates constant so that we can reabsorb and secrete things along the rest of the renal tubule and the nephron to make adequate urine and save what we need to. So autoregulation is going to be the ability of the kidney to adjust that filtration rate so we keep it constant, which we will look at in a new video.